Hi, I'm Matt Malkan, and this lecture is about the lives and the spectacular deaths of unusual, high-mass stars. Now, this is for the Astronomy 4 class at UCLA, which, to remind you, is a general education class for people who are interested in astronomy, but not really undergraduates who are majoring in physical sciences. So we'll be fairly qualitative. We won't go through any heavy equations in this lecture, but I do want you to get a good physical picture for why all these remarkable and very important things, important even to us on Earth, happen when an unusual massive star evolves and reaches the end of its spectacular lifetime. So we have a number of goals for learning in the lecture today. We need to be clear on what is special about these unusual massive stars that leads to a different life, a different evolution, and particularly a different ending from normal stars. The most common stars like the Sun, which are less massive, have less gravity. And we need to understand how heavier elements than carbon nuclei will be produced as a result of the lifetimes of these massive stars. That makes them extremely important to us personally. We want to understand in today's lecture what the steps are, the mechanics of how these stars explode as supernovae. What does that actually entail? And we'll get some appreciation for how dramatic the events are in a supernova, really some of the most spectacular bangs since the Big Bang, and in particular the sources of many of the elements that are absolutely vital to life as we know it, certainly life on Earth. So that's a lot of exciting goals today. But first, we need to remind ourselves of what we already are supposed to know about the evolution of normal stars like the Sun, fairly low-mass stars. And I will get the next slide with there. So the main difference, of course, in any stellar evolution is going to be how much gravity it has. In other words, how much total mass the star has. We've already seen that that really determines all of the main things you need to know about a star. In particular, it determines how hot the interior, the center of the star is going to be, and that determines how much nuclear power it's going to generate on the main sequence. That determines how fast it burns through its fuel supply. So the main sequence, as we saw earlier, is really a mass sequence. Now, in today's lecture, I'm only considering the upper left end of the main sequence. Those are the stars that are very hot on the main sequence. They're burning their hydrogen fuel at a furious rate, so they're very luminous, but they don't live very long at all because they'll burn through all of that fuel much, much faster than the Sun. Millions of years instead of billions of year lifetimes on the main sequence. So that's the first important difference, and this difference carries through because the ability of the more massive stars to have a stronger gravity, which of course is going to make their interiors more compressed and hotter, that's hydrostatic equilibrium, we saw that on the main sequence, is also going to carry through to their final stages of evolution. Now they're going to go through the same final stages of evolution that normal stars like the Sun do, just faster. So the Sun, for example, spends most of its time, more than 90% of its life, on the main sequence, just burning hydrogen fairly steadily into helium, and then it's stuck temporarily while the helium ashes of this hydrogen fusion reaction are just sitting around waiting to get ignited at a very high temperature, much higher than the star has been operating at 15 million degrees. But the star, the Sun star, or any of these stars, will compress and contract because the gravity, intense gravity that's always pushing everything down to the center of mass, is very patient, and it has been waiting. It's been waiting for the opportunity. It's been waiting for when there wouldn't be as much pressure to hold the star up. For example, when it runs out of nuclear fusion power in the core, and as soon as it has its chance, it's going to crush the core more and more compactly to a higher density and a higher temperature. Now we know in the sun, this process then, while the core is getting crushed, the gravitational potential energy is being transferred to the outer layers, makes a very dense core, but paradoxically, a very extended, low density atmosphere of the star. It turns into a red giant temporarily, and it's only at that point burning hydrogen, fusing it into helium. That's what I call burning. It's a fusion reaction in a shell of fresh hydrogen that's available outside of the helium core, which is now getting hot enough to burn. So all of these stars are going to go through their first red giant phase. Then how does that terminate? It's the same story for all of these stars. It eventually gets hot enough in the core. What's the magic temperature? Around 100 million degrees, where you have this remarkable reaction that we talked about earlier, where 3 helium nuclei, that's called alpha particles, before we knew they were helium nuclei, 3 of these atomic mass 4 particles at about the same time collide, come together in a rather improbable but very fortuitous fusion reaction to make 12 atomic mass units, which is a carbon nucleus. That's the end of the line for most stars. That's all they can do. But the more massive stars, and then it will go through a red giant phase again when the carbon core just compresses and is condensed, and finally, eventually, is so compressed to such a high density, but no nuclear power being produced, that it leaves behind an electron-degenerate core, which will be the center of a planetary nebula. It's going to become a white dwarf. So that's the end of the line for most of the stars. Why? Because they never managed to pull the next trick. It's like pulling a rabbit out of a hat. They ran out of rabbits. There were no more tricks for the sun because they couldn't get hot enough to take the ashes of the previous fusion reactions, namely carbon-12, and have a more advanced nuclear reaction. Now, why would that be hard to do? Well, think about it. It's all the question of how hard it is to overcome the electric repulsion of positively charged ions in this plasma in the center of the sun. And the problem is that carbon with 12 has 6 protons. And so if you want 2 carbons to get together, that's 6 times 6. That's 36 times the electric repulsion of 2 protons. So that's going to usually be too strong a force to overcome. Even just getting a carbon with 6 protons to combine with a helium. If there's some of those left over, 2 protons, that's 12 times, 2 times 6, 12 times the electric repulsion of the proton-proton reaction. And so it's going to require a much, much higher temperature, even much higher temperature than it was to get 2 protons to stick together earlier on. And the sun simply doesn't have enough gravity to ever get to that high temperature. The massive stars do. This is unusual, but that's what makes them special. So I've sort of outlined a whole series of increasingly complicated, more advanced nuclear fusion reactions that are going to go on in the more massive stars, where each of the earlier ashes of a previous reaction then becomes the nuclear fuel to combine and make ever more massive nuclei, releasing decreasing amounts of nuclear fusion power at furious, faster and faster rates. So if you wanted to imagine what this massive star would look like, it's going to have more than just 2 red giant phases like the sun. It will have multiple red giant phases. The red giant phase is every time the nuclear fusion source, whatever the reaction is in the core, shuts down and the core compresses down more and more, the outer layers puff up, you get a red giant phase. Then the temperature gets so high, ta-da, a new nuclear fusion reaction, a more advanced reaction, will come along to save the day and keep the star's core burning and generating fusion power, but just for a short time. This is a short-lived victory, because then that fuel source will get used up very quickly, another red giant phase, and then maybe a new nuclear fusion source will temporarily switch on for a brief time to make the star a blue star, because it will shrink back down as the core is burning with the new fusion reaction. So it goes back, and these are all, and of course, they're all of the different shells the hydrogen burning shell, then a helium burning shell, will still be eating their way out through the fresh material in the outer parts of the star. So all of these energy generating reactions at the same time at very high rates, because at the high temperatures mean these stars are going to be the most luminous stars around, very exceptional. I wouldn't even call them giant stars. They'll be called supergiant stars. They started out being extremely luminous on the main sequence, and they just get more and more luminous, swinging back and forth from a red supergiant to a blue supergiant, then to a red supergiant as a new core fusion reaction is exhausted, and so on. So what you're looking at, let's see if we can see this in the next slide, is a kind of an onion layered appearance of the interior of the star. So let's look at the nuclear reactions first. This is just a sequence of them to show you how progressively more and more complicated nuclei get built up. So we start here with 12 carbon. That's as far as the sun goes. End of the line here for the sun and most stars here. Can't do any more. However, at a very high temperature that the sun is unable to achieve because of its insufficient mass, a helium nucleus with +2 protons there could collide and stick. Well, 12 plus 4 makes a familiar, stable atomic nucleus. 16, that's 8 protons and 8 neutrons. You don't even have to change any of the neutrons or protons from what they were in the input products to get a stable nucleus of oxygen 16. You're thinking, well, that's a nice idea. Too bad the sun can't do that. Yeah, because, well, you might have thought that the sun was doing pretty well to get up to 100 million. That's 10 to the 8 degrees in its core, where the triple alpha reaction fuses helium into carbon. But that's not nearly good enough. This reaction, because of the enormous electric repulsions here, requires that these carbon and helium nuclei are moving much faster with enormous energies, and that only happens that some of them are going that fast at, wait for it, 600 million degrees, give or take. There. At 600 million degrees, these fusion reactions can take place, and they'll take place very rapidly, producing oxygen, and then it'll all be used up, and then there's no carbon left. There's a little bit of helium left, but no carbon left, and the star is once again looking around. That was a neat trick. I've come up with all these tricks: burning hydrogen, burning helium, burning carbon. Now I got a bunch of oxygen. Well, you don't have to have too much imagination. I don't know if these stars have a lot of imagination. I guess the next trick here would be if we could overcome even the repulsion between helium nuclei and oxygen with 8 protons at a higher temperature. Let's just crush that core down with the very patient and what's the word for gravity? It just never stops. It never goes away. It's like irresistible here. Will then allow heliums to be captured by oxygen. It's a series of helium capture reactions to make an atomic nucleus with 10 protons and 10 neutrons, which you might not know what that is. That is the 10th atom in the periodic table of elements with an atomic mass of 20. It's neon. So you'll have oxygen burning into neon. Now remember, at each one of these, and then of course at a higher temperature, now we're going to be getting up to billion degrees or more, even helium will be able to capture, it will overcome the electromagnetic repulsion, the electric repulsion, and capture another alpha particle to make something with 24 masses, 12 proton, 12 neutron, which is magnesium. So we're burning neon into magnesium. And then at even higher temperatures, and even at some of these other temperatures, a number of more complicated nuclear fusion reactions could take place. For example, if there's some carbon and oxygen around at a very high temperature, now we are talking about well above 1 billion degrees here, you could go directly into silicon with 14 protons and 14 neutrons, atomic mass of 28, or you could have 2 oxygens and going to sulfur, you could have, and finally, the ultimate reaction, and we'll see why in a minute, the end of the line, it's down here in the lower right-hand corner of the figure, because there's no point in putting anything else after this point. We combine 2 silicons here to get 26 protons and 30 neutrons, or iron 56. And that's it. This is a pretty complete diagram here. I didn't leave out anything. But this is cyclical, so fuel source is exhausted, new thermonuclear fusion power ignites in the core. Then that's exhausted. Then a new fusion power source ignites to burn oxygen neon. Then that's exhausted. Then neon becomes the fuel to burn in magnesium, and so on. So that is why, as I said earlier, you're going to swing back and forth on this HR diagram as one fuel runs out and it becomes red giant. Then a new fuel ignites in the core. It tries to swing back a little bit, and it can swing back a few times here. Honestly, though, there really isn't very much time for the outer layers to adjust. Why? Because in the end of this, for these really massive stars, look, we know of some stars that are almost 100 times the mass of the sun, maybe more. All of it happens so fast inside. Everything I just said right now, all of those different advanced nuclear fusion reactions are going such a short fraction of the star's massive star's lifetime that the outer parts don't even really adjust. It's just a supergiant star that's very, very luminous. Look at these things. These are 10,000 to 100,000 times, maybe even hundreds of thousands of times more luminous than the sun when it was on the main sequence. So an example of a massive star that's a red supergiant phase right now, a very short phase in the lifetime of a massive star. Already unusual to have a massive star anyway. Now we're catching it an unusual phase of its unusual lifetime would be Betelgeuse. It's one of the brightest stars in the sky. That's a red supergiant, and that means it is in the process of running out of nuclear fuel in its core. It is very much reaching the end of its lifetime. And very interesting to think about what's going to happen next to that star. And it's not going to be dull. So that's what's happening to the outward observer. We'll look at these stars during this brief period. By the way, even though this is a rare period of rare stars, there's quite a number of them visible to the naked eye. Why? Because they are hundreds of thousands of times brighter than normal stars. So you can see these things at vast distances, even without a telescope, whereas you could not see the vastly larger number of more normal low-mass stars. So as I said, if you could look inside, which we cannot, but if you could imagine, you could do a core sample through the center of this very highly evolved massive star, it's going to start building up layers a bit like the skin of an onion there. And so finally, for a supergiant star that's very massive, really at the end of the line here, the core of the star has, through nucleosynthetic, that's nuclear fusion reactions, has produced the heaviest nuclei that it's capable of doing in this fusion configuration, which is iron 56. You will see that I appear to have an obsession about iron 56. Well, it's not me. The universe has a thing about iron 56. So that's the end of the line here. And in a shell around it, though, the temperatures are at least high enough to burn carbon and oxygen, and they have not all been converted into magnesium and neon and iron. So there's a shell that's burning that. Outside that, there's carbon and oxygen, which is not hot enough. So it's just waiting to fall in here. Eventually, this shell will march out and maybe burn some more of the carbon and oxygen into more advanced fusion reactions. Around that is a helium-burning shell, which only has to be 100 million degrees. These are billions of degrees in here. 100 million degrees that air, and outside that is helium that's not yet hot enough to burn. Then there's a hydrogen-burning shell. So these first two shells looks just like the sun is going to look like, your normal red giant star. And as I've emphasized before, the technically correct term that astronomers, when they want to prove that they really are professional astronomers, we don't call them red giants, we call them shell-burning stars. And indeed, the sun will be a shell-burning star. It's just these massive stars have more shells in there. And more of the material is passing through to the hotter regions and getting more and more advanced nuclear fusion going on. But there's a number of problems with this, I have to point out. Let's go back to that previous slide that showed the fusion input products of the reaction and then the fusion output product. And we all know from our experience with fusion reactions in the sun, thermonuclear fusion, the reactions what is the condition for this reaction to produce energy, to release energy? We have to add up the mass going in. We have to compare that with the mass of what comes out. Or we could look at this reaction, add the mass going in, an oxygen and helium, compare that to the mass of the neon, and what condition must be satisfied to get any energy out at all? The delta M has to be negative. In other words, the mass coming out has to be smaller than the mass going in. And you can look it up in your atomic nucleus table if you happen to have one. Yes, the mass of these two things is a little bit higher than the mass of this. The mass of these two input products, oxygen and helium, is a little bit higher than the mass of neon 20, but not by much. So that's the only part that actually gets converted into energy. Remember, E equals mc squared. In these reactions, that's Einstein's famous formula, it really means E equals delta mc squared. It's only the change in mass that gets converted. And by the time we get up to these reactions, the delta M is a fraction of 0.1% of the total mass involved. So most of the fuel is not converted into pure energy. Only a decreasing, diminishing little small fraction, part in 1,000, less than a part in 1,000 of this is actually converted into pure energy by multiplying that delta M times c squared. And you're going, yeah, that's too bad, but c squared, c is a big number, the speed of light squared is a huge number, so we're still going to get some power out of this. And you're right, you are going to get some power, but this star is burning these products at such a rapid rate that it's just not going to last very long. So I have to say that all of these nuclear fusion reactions, if you wanted to get emotional about it, it strikes me as pathetic attempts to put off the inevitable. You know, this star is just not willing to deal with its ultimate mortality here, so it just keeps on coming up with fancier and fancier games to only temporarily and even very briefly put off the inevitable death. And the inevitable death is down here in the lower right-hand side of this diagram when you get to iron 56. So this star has been basically producing less and less long-lived energy sources, rather desperately, and then it ends up with something which is not an energy source at all. Iron 56 is the one atomic nucleus that cannot be a nuclear energy source. Why not? There's something special, as I told you, about iron 56. It's the most stable nucleus in the universe. What does that mean? Let's think about it a little bit. What does the most stable atomic nucleus mean? We think, wait a minute. I've still got some lighter nuclei around. I got some heliums. I've got some carbons or something. Why don't I just fuse them? Well, you could do that if you, maybe under some conditions you might be able to do it. Get something to stick to iron 56. Make something heavier. You know, make silver or something. That sounds like fun. Or gold nuclei. There's a problem here. You could do that under the right conditions. You've had a huge amount of energy, because the mass of the nucleus that you will produce when you combine and fuse something to iron 56, oh no, will be more massive than what you started with. So the products that you go in, like iron plus oxygen or iron plus helium or whatever, will actually have less mass. That reaction is not going to generate any energy at all. Now delta M is going to be positive. You're actually producing more mass. Oh my gosh, you know how this goes. That means you need to consume energy. Delta M can only be produced in these advanced fusion reactions by taking away energy, a lot of energy, delta mc squared, from somewhere else, basically from the energy of these nuclei, the heat in the center of the star. So that's a terrible idea. Iron 56, if you fuse it, if you could do that, you've suddenly just figured out a way to actually consume energy. Congratulations. That's the opposite of what this star needs to survive and have energy to support itself. Okay, that was a bad idea. Sorry, I even thought about that. I don't know. maybe we could try another trick. This is getting to be a fairly big nucleus. It's got 56 atomic particles in there, 30 neutrons, 26 protons. That reminds me a little bit of some of these really massive heavy nuclei. You know, like uranium-235. That thing has 235 particles in it. What strange, interesting nuclear reactions spontaneously happen with uranium, for example? It has such a big nucleus that it will spontaneously, without even doing anything to it, just sitting there on your desk or whatever, sitting there in a reactor, for example, it will spontaneously split into smaller pieces. So that would be nice, because in the case of uranium, the smaller pieces have less mass than the original uranium nucleus, and so you get nuclear power out. It's called nuclear fission power, and that's how atomic reactors work at the moment. And if you really run it really fast, and then you can get a lot of atomic power out in one shot, which would be an atomic bomb, a fission bomb. That's hard to do. You need to have one fission reaction trigger and stimulate more fission reactions in a chain reaction. But so it took humans a long time to figure out how to do that. And fortunately, it's fairly difficult to do. But this completely different situation. Don't even think fission power with iron-56, because the opposite will happen. It's not like uranium. Yes, under the right circumstances, again, if you want to, you could break iron-56 up, for example, into those pieces of silicon. Remember, you could run the reaction backward. But what would the point of that be? You're going the wrong way, because the pieces that come from splitting or fissioning iron-56 have, oh no, more mass than the iron-56 you started with. It's the opposite. It's not producing power like splitting uranium. It's sucking up more energy here. Actually, the delta M is positive. More mass would have to be created out of energy from somewhere. You'd have to get the energy from whatever temperature of the motion of the particles that already exists. So we can't produce any energy by fusion. We just will be consuming energy if we have fusion. We can't produce any energy from fissioning iron-56. It is a freaking dead end here. This is terrible, because it is, as I said, the most stable nucleus. All right, so just to show you real numbers here, because I think people don't this kind of shocked me. This is for a very massive star here. This is a model prediction based on our understanding as best we can of stars. I don't think anybody has really directly ever actually seen these exact fusion reactions. You know, we have indirect experimental verification of these, and it all happens so fast. So you have a massive star, maybe 15, 20 times the mass of the sun. There are not very many of those. Just a small percentage of any stars ever have that much mass. But they will be able, for example, to take their carbon, burn it into oxygen. But the lifetime there, the star was millions of years on the main sequence. All the carbon is going to get used up, burned into oxygen through fusion reactions in not millions of years, but just thousands of years. And then these next more advanced fusion reactions leading up to neon, leading up to magnesium, leading up to silicon, those reactions, it probably took me almost as much time to describe them to you as the star actually has increased its lifetime by. It only buys the star a matter of years of extra lifetime. Pretty sad. And the final reactions I told you about, when silicons, 28 silicons, combine and fuse into iron, it's the last chance of that star to save itself and generate any nuclear fusion power to hold up its core. It's all gone in a matter of days. That's it. The star that had been living for millions of years is going to reach the ultimate crisis. It's the ultimate energy crisis. They tried everything in that star. You have to give that star credit. I mean, if they were not inanimate objects, that star tried really hard. Good for you, but you lost. And now it's time to pay the price. You've just got this useless core of iron-56. In fact, it's a little bit worse than useless. what's going to happen? So now the star has just this iron 56 core that's not generating energy. It's crushed more and more dense. The pressure goes up. Gravity was waiting. Gravity rules. Gravity's in charge here. Gravity keeps crushing that down to a higher and higher temperature. It was billions of degrees. Eventually, it's going to go up to a rather critical, very disastrous temperature of about 3 billion degrees. Why is that a disaster for the iron core of the star? It's a disaster because suddenly the energy of the reactions, well, suddenly the iron nuclei become, let's take that message out. I don't want to say that. Okay. There. The iron 56 now is able to use the energy at 3 billion degrees. In other words, I don't know if you're a chemist or whatever, it's now able to consume energy rather than produce energy. There's when you cross 3 billion degrees, the iron 56 will rather suddenly start. All of this happens at once. It will start higher advanced fusion reactions, taking away the energy that's there. It will start fissioning reactions. They'll be broken apart by the gamma rays that you get in a 3 million degree black body here. So, but all of those reactions are taking away, removing energy from the core of the star. So it's like the anti star. It's not producing energy now. It's consuming all the energy that's in there. And now you're thinking, okay, so all the energy is getting consumed. Well, I'm thinking back here to the sun. I guess it'll just settle down into an electron degenerate state of matter where all the electrons are basically touching in their orbits, and they're not allowed to occupy the same orbits. So the electron degeneracy pressure will settle this thing down, I guess, as some kind of big old white dwarf. Wait a minute. We already went through this in an earlier lecture. We're talking about massive stars that began their lifetimes more than 8 times more massive than the sun. And so even after the end of their lifetime, they've gone through many red giant phases. They've lost a lot of their outer layers of mass. A lot of that has been blown away into interstellar gas there. But there's still going to be, at least half of it will be left, or at least a third of it will be left. What's the Chandrasekhar limit? You better remind yourself of this. That's the maximum allowed possible mass that an electron degenerate star, a white dwarf, can have before its gravity overwhelms electron degeneracy pressure. Because electron degeneracy pressure, remember, is not infinitely strong, basically because electrons really cannot go faster than the speed of light. That's as fast as they can go, and they're not allowed to go any faster. And so, in fact, we saw as a star, well, remember what the Chandrasekhar limit is? It's not that much above the mass of the sun, 40% more. So as you get white dwarfs that are more massive than the sun, and there certainly are some, 1.1, 1.2 times the mass of the sun, 1.3 times the mass of the sun, those white dwarfs, paradoxically, are actually smaller and smaller. They're a good bit smaller than the Earth. The most massive white dwarfs are barely stable. A little bit more mass and gravity, and there'll be no stability at all. And that is what we're looking at here. At the end of the line of a massive star lifetime, we're looking at a star which is too massive, too much gravity to stabilize as a white dwarf. What do you think happens then? Can't be a white dwarf. Gravity's going to win. Gravity must win. All right? And the reason gravity must win is because we are not going to disobey. We cannot violate the Pauli exclusion principle for electrons. They just will not tolerate it. Not allowed. It's not just a suggestion. Is not allowed. They will not do it. All right, so what's going to happen? So suddenly, really, this happens rather quickly, probably in a matter of minutes. Incredible. I don't know, an hour or something, all of the iron starts fissioning and fusing at the same time at 3 billion degrees. All of the heat of the star has gone away. There's nothing holding it up. It's exactly like, the center of the star there has been holding up, I don't know, it's like a gigantic stack of weight on top of it that's barely been able to hold up for many, many years. And suddenly you just pull the rug, you pull it out from under it, and all of those weights, all of those upper layers of the star that were held up there in a hydrostatic equilibrium, now there's no hydrostatic equilibrium. It all implodes. And it implodes at an increasing speed as it falls down. This stuff is coming down in there at something like the speed of light. And it's not going to be stopped by electron degeneracy pressure. Why not? I told you, the electrons can't handle it. They can't go faster than the speed of light. In fact, just to show you how serious the electrons are about refusing to occupy the same state with other electrons that are pushing them around, which is exactly what they're faced with here. Okay, you electrons, we got more electrons falling down here every second now on you. What are you going to do? What are the electrons going to do? They say, this is an intolerable situation. We will not accept it. We would rather not exist as electrons than violate this fundamental principle of physics, of electron physics here. It reminds me very much of those samurai movies where the heroes, well, they're just very stubborn basically and very tough, are compressed into an intolerable, insufferable situation, and they end it basically by ending themselves. They're samurai electrons. And, a lot of those samurai movies are very over the top, but I think all of us kind of admire those electrons for sticking to their principles. And their principle is, we're just going to go around somewhere, don't have to look very far, find a proton, and bury ourselves into it. There's your one reaction here. That's an amazingly unexpected nuclear fusion reaction. See that down there? That is electron plus proton. This is a completely unnatural reaction. This should never happen under normal circumstances. An electron plus a proton goes to what? Well, you have a minus charge and a plus charge, so it goes to something with approximately the mass of a proton, but it has a zero electric charge. It's neutral. It's a neutron. What a weird, weak nuclear force reaction. Changes a proton for a neutron. Now, we've seen these happen before, by the way, inside nuclei. It just requires extreme conditions. But wait a minute. Whenever this can only happen, the neutron-proton change back and forth. This is called inverse beta decay, because a beta decay is when a neutron decays into a proton plus an electron. That would be beta decay. It gives off a beta particle or an electron. And that had already been seen. This is the opposite. This is going to produce a neutron and wait a minute. There's an enormous amount of energy involved in this. It's a weak nuclear force reaction, so that means a weak nuclear particle of very low mass, almost no mass at all. No normal reactions would matter, no electromagnetic reactions, no strong nuclear reactions. It's like a ghost particle. The ghost particle of weak nuclear reactions, a neutrino, is produced here. A high energy neutrino. So basically, what happens here? In a matter of seconds, in probably less than a minute, all of the energy in the center of that star is converted, because every single electron will find a proton. There's about equal numbers there. They will all turn themselves into neutrons plus neutrinos. Every particle in the interior of the star. The whole thing becomes a humongous ball of neutrons. It is suddenly neutronized, and all of the energy goes into these neutrinos. And just think about how many nuclei there are in a massive star. One very high, extremely high energy neutrino produced for every one of those nuclei in a matter of seconds. We could actually work out the numbers here, and you'll realize, holy crud. For those few seconds, the amount of energy, and then it's going to try to escape from this star. And neutrinos are pretty good at escaping, but they're going to have some trouble bouncing around because there's so much stuff above them. You know that they can pretty much go through a light year of lead, but there's much more than the equivalent of a light year of lead above them because the stuff is so dense. So they will bounce around, they'll try to get out, they'll try to escape. During those seconds that all the neutrinos got produced, more energy is being released from this star, this dying massive star. More energy during that period of a few seconds is being released than all of the energy released during those seconds by all other stars, not just in that galaxy, not just in the Milky Way. All the other stars in the entire visible universe are producing less energy in those few seconds than just the energy of just these neutrinos coming out of the nucleus of that star. That is truly one of the most awesome events that ever happens in the history of the galaxy. It's a supernova explosion. So most of the energy you don't actually see directly. It mostly comes out in neutrinos, which we're only able to detect recently. And guess what? You'll be very happy to know they were detected from a supernova. So this is correct. This almost sounded like science fiction here. It's kind of hard to believe. You're just going, yeah, that's a really fancy theory. What a story. You got any data on that? There was no data, no real direct data until 1987. When we actually caught the neutrinos from a nearby supernova happening that were produced exactly as I've said here in a core collapse that neutronized an entire star. So yes, it does happen. And during those seconds, yes, it was more luminous, more powerful than everything else in the universe put together, which helped us to have a chance of detecting its neutrinos. That's what a supernova is. Now we'll look at what the effects of a supernova are in the next lecture, because of course all this energy is going to blow out in a spectacular fashion. And although the neutrinos are the main energy, there are these interesting sideshows, like exploding the outer layers of the star and producing a huge flash of light. That's a sideshow. We might see it. And producing all of the heavy elements that are heavier than iron 56. And spreading them out all across the galaxy to where they could make the next generation of stars and planets and eventually people.